A 3D model of a factory floor without a live data connection is a video game. It might look impressive in a boardroom, but it lacks the functional utility of an engineering tool. A functional digital twin reacts in real time to the physical movements happening on your actual production line. Building this requires a 3-layer architecture. We will use direct PLC access for the physical layer, a Python environment and Firebase for the data pipeline, and FlexSim for the virtual representation. If any single layer of this architecture is disconnected, the system loses its ability to mirror reality. We have to start at the foundation. Layer 1 is the physical asset. We begin on the factory floor with the specific hardware you intend to monitor. To get accurate data, you must tap directly into the machine's programmable logic controllers, the PLCs, and its physical sensors. This removes the delay and inaccuracy of manual operator reporting. This provides raw telemetry straight from the source, exact cycle times, spindle speeds, temperature readings, and vibration frequencies. While this data is the foundation of the twin, it is currently trapped within the machine's local memory. Moving that data to a usable environment requires the second layer. Layer 2 is the data pipeline. This is the most common point of failure because it requires translating proprietary industrial protocols into web-friendly formats, a task that often stalls due to IT silos or hardware incompatibility. You can avoid the high cost of custom on-premise servers by using lightweight, modern scripts to handle the transition. A Python script can be configured to listen to the machine's sensors, grabbing new data points every millisecond. The script then pushes that data directly to a real-time NoSQL cloud database, like Firebase. When the connection is live, your cloud database will show numerical values flickering and updating every fraction of a second as the pipeline delivers new packets. Your physical machine is now officially live on the internet, providing a globally accessible data stream for the final layer. Layer 3 is the virtual setup. This is where we integrate 3D simulation software, like FlexSim, to visualize the data. You must configure the simulation software to read the Firebase database. It uses those incoming numbers as direct triggers for the virtual components. This creates a direct sync. If physical machine speed drops by 10%, the database updates and the 3D virtual model instantly decelerates to match. If a sensor detects a jam, the data immediately halts the virtual model, flashing a warning signal. The 3D model is now a live representation of your facility, reacting to real-world physics and data as they occur. This architecture provides a specific strategic advantage, the ability to run predictive, fast-forward simulations. To test a future scenario, you first sever the live data feed. This stops the model from simply mimicking the current state of the factory. You can then manually input specific variables, such as a hypothetical 20% increase in production volume for the following month. By running the simulation far faster than real time, the system can identify exactly where the production line will bottleneck under the increased load. This identifies which machine is likely to fail before the change is ever implemented. You can troubleshoot multi-million-dollar crashes in a virtual environment today, so they never happen on the actual factory floor next week. Now that the live clone is running, the system is generating millions of granular data points every day. It tells you what already went wrong. Click the next video to see how to apply machine learning to this data stream. We will show how to use these patterns to anticipate downtime before it occurs. The value of this architecture lies in shifting from historical reporting to predictive maintenance. I'll see you in the next video.